This is chapter 18, planar kinetics of a rigid body, work and energy. We learned about kinetic energy of particles in earlier chapters. Here we'll learn that bodies, as they rotate, also carry kinetic energy. So is the translation and rotational kinetic energies that we're going to deal with in case of rigid bodies. So if we are assuming a body to be a collection of small masses, infinitesimal masses, and we take as the kinetic energy the energy of the small infinitesimal masses with their velocity squared taken half, like we learned in systems of particles, and the kinetic energy, total kinetic energy of the body as it's moving, performing both rotation and translation. We have the velocity of a point B, and we associate the reference frame to the point P. Again, the total kinetic energy will be an integral of the kinetic energies of the infinitesimal pieces of mass. So this will be the small mass dm. Okay, we can write, knowing the distance to the small mass and knowing the velocity of point P, we can write the velocity of the piece of mass dm. And so velocity of I is velocity of P plus velocity of I with respect to P. And when we square it, there are some terms that they're going to simplify out. So the earlier equation for total kinetic energy becomes, or takes this form. So the first term here, integral of dm over the entire body, that's the mass of the body. So first means the kinetic energy of the body as it's moving, or the velocity Vp of the point P. And then we have this last term, and this is integral over the entire body of r squared times dm. This is the moment of inertia of the body relative to point P. And then the other two terms in between, these are the velocity of point P, and so some cross terms here. The convenience of the equations for kinetic energy is where point P coincides with the center of mass. In that case, the centroidal distances are going to be 0, and these terms in between are going to be both 0. So kinetic energy, total kinetic energy of a body, is the mass of the body times the velocity squared divided by 2 velocity of the center of mass plus half of centroidal moment of inertia times omega squared. Okay, so the body, as it rotates, carries kinetic energy. You're familiar with flywheels, I'm assuming. They store kinetic energy as they are spun, accelerated, or as they spin, they carry kinetic energy, and that can be released by slowing down. There have been experimental vehicles that store energy in large flywheels, like buses. You can Google and read about flywheel energy storage, and for stationary applications. Okay, and then say you accelerate your automobile or car or truck. It's not just the translating mass, the weight of the or mass of the vehicle, but also you consume energy to increase the rotational speed of everything that's engine parts and flywheel and transmission parts and the wheels of the vehicle themselves. Okay, for the translational case, kinetic energy is half of the mass times velocity of the center of mass. If we have a fixed axis, kinetic energy is going to be rotation about a fixed axis is going to be half of mass times velocity of the center of mass plus half of the mass moment of inertia about the centroid times omega squared. And the we learn of the parallel axis theorem, and we can combine these two by saying that for rotation by a fixed axis, kinetic energy is half of the moment of inertia about the axis of rotation times omega squared. Okay. Of course, if you have rotation about a center of mass, and that's the desired way because it will correspond to a balanced rotational body. You don't have any reaction of the support caused by the center mass being offset. Then this first term is vanishes. But otherwise, if the center mass is offset from the axis of rotation, this will be the kinetic energy. And then if we have general planar motion, there's the early equation 18.2. It's repeated here. So kinetic energy of the center of mass and then kinetic energy of the rotation of the body, the way half of mass centroidal mass moment of inertia times omega squared. We can write the kinetic energy of a body relative to the center of instant center of zero velocity, and that will be a case where the translational kinetic energy is combined with the or just because it's zero velocity, so it'll be like the point P equation earlier, but point P equals 0, and then velocity of point P. So maybe I should go back. So if we make P the instant center of the body, center of zero velocity, then on one hand the velocity of the instant center is 0, and then so whether squared or not, it's 0, and we're left with just this part. Okay, and of course we can have systems of interconnected bodies, and will be the kinetic energy of the component bodies that may occur in problems, and we can use them as such. All right, work of a force. This is something that we have seen in part in early chapters. So an external force that's applied, and you have the point of application of the force moving, say, on a curvilinear path. The work is an integral of this dot product force vector times dr, and it takes this form, so dr becomes ds, and then force has to be it's only the component in the direction of displacement that creates work. Okay, so if the force is constant, then the work of the force is going to be this constant force cosine theta. So constant, yes, but not necessarily aligned with the direction of motion of the body. Cosine theta times s, the curvilinear displacement. Weight, work of weight, is negative of the weight force times the vertical displacement. And then if we were look at the spring, the work of a spring is the difference in, we recognize these from early chapter, the potential energy of the spring. So we have positions S1 and S2, and then the work between these two positions is this difference. So the next section talks about forces that do not generate work, and they're if we have firstly, internal forces don't do work. If you have reactions at a joint, there's always going to be an equal and opposing force, action and reaction. They don't do force. They don't do work. Okay, then we have friction force of a body that is, or a disc that rotates without slip. Then the friction force does not produce work, and normal force is not producing work. This is more intuitive, so center of application of the force N is not moved in the vertical in the direction of the force, only perpendicular, so clearly no work. Force F, though, the friction force, appears to move, but actually it's moving along the or it changes the point of application on a new location of the rolling disc, and again does not produce work. If we have a couple, he calls it couple moment. So if we have a couple, the work of the couple is can be analyzed as the work of the of two forces at a distance r, chosen such that F times R equals M. So if we have a rotation by angle theta going with the moment, then the work done will be ultimately we'll see it's M times the angle theta. But infinitesimally, we can say F times the one and the other of the forces and half of the radius in between. So work of each force ends up being the infinitesimal work of the force moment times d theta, small increase, small change angle theta. If you integrate between two finite positions, theta 1 and theta 2, and if this moment can change as the body rotates, or if it's fixed, that is not changing, it comes out in front, and the result that I anticipate, where I say it's moment times theta, that corresponds to the case where moment is constant. Okay, so moment work of a constant moment is m times final angle minus initial angle in radians, so they have to be in radians. Okay, there are some sample problems. There's one here where we have the work of gravity and work of a spring, and then there's section 18.4, principle of work and energy. And we're familiar with this kind of equation. So if we have two states of a body or system of bodies, the initial kinetic energy plus the work done is equal to the final kinetic energy. Or you can say the work done by the external forces is the difference in between the final kinetic energy minus initial kinetic energy. Okay. And he's repeating something I said earlier: forces that do not produce work, and the internal forces are mentioned here. Okay, there's a number of problems going with this first part of the chapter. Let's go to section 15.8. That's page. Let's see, we're at page. You're page 496. Conservation of energy. Okay, so we had earlier the work energy equation. Now, if the external forces do not produce any work upon the body, so early equation 1814, the sum of sum of U1 minus U2, the work of the forces is 0, then the energy, it's conserved. Initial and final kinetic energies are conserved. The case of gravitational potential. The gravitational potential is we choose a reference. Vertical, so acceleration to gravity is most cases going down along the vertical axis, the y-axis, we're looking at the elevation of the center of mass of a body relative to a fixed horizontal line, the datum. And the gravitational potential is weight, mass times acceleration to gravity, weight times the elevation of the center mass. Okay. So in between two positions, before that, there's the elastic potential energy. Elastic potential is equal to half of spring constant times the stretch squared or compression squared, measured from sign does not matter once it's squared, but it's measured from the unstretched position. So it's essential to measure S from an unstretched position. Datum, you can choose it anywhere. Conveniently is to take it at location elevation that is below any of the configuration of the system, but could be in between. Okay, could be ground level, knowing that will never the particle will never go below ground. Although you can have a pit of some sort, and in that case you could take it at the bottom of the pit. Okay, so conservation of energy. The total energy of a body is the gravitational elastic potential. There are other conservative forces. By the way, what's conservative force is gravity is one and elastic energy is other. So the work done between two configurations is dependent only on the initial and final configuration, not on the path between them. So you start at this location, and whether you go straight or horizontal, then up, or on a curvilinear path, the work of the gravity, it depends only on the, and of course if you rotate the body in between, although that should be due to other than the weight of the body itself. So say maybe there's aerodynamic drag or an initial spin. Okay. So yeah, conservative force work done depends only on the initial final configuration. So we have this conservation of energy, stating that gravitational elastic potential is a constant, and if there's no work done between two configurations 1 and 2, then no work of some external forces. You have only or other than elastic and gravitational potential, or elastic and gravitational forces, then the energy is conserved. Okay, you may have an exchange of energies between kinetic and potential, but there are some other given configuration 1, 2, or other configuration. It should be the same. Again, provided that you don't have any non-conservative forces acting in between, like friction or other non-conservative forces. Okay. He has here, as in many other places of his book, procedure of analysis, and identifying the center of mass, if it's potential energy or elastic potential, choosing the reference, the datum, the right way. Okay, and if there are no non-conservative forces involved, then the energy is conserved. Okay, so I guess this is the chapter on page 511. 511. He has a summary of or chapter review. So kinetic energy for translation, rotation about fixed axis, general plan motion, kinetic energy, and then work of a couple. Interesting. Here it shows the path between the initial and final configuration. So I would say this is a better figure than the one in the chapter. Okay. And the work of gravity is positive one if you work with W. If you work against W, the work is negative. So going from a high elevation to a lower elevation, the work of gravity, it would be a positive one. So you can apply as this is, but recognize that delta Y becomes negative. Okay, and so yeah, a good place to come for a summary of equations, and there are some review problems. Okay, so this was an introduction to this chapter 18. We're going to solve some problems in class, and with this I'm stopping the recording.